Hey, everybody. Happy Thursday to you. I'm recording this on Tuesday, so actually, some of the tests are done, some are still coming in, but I certainly haven't had a chance to look at them yet. And since I've already received a couple apology emails from some of you saying, hey, Mr. Crowett, the graphs were a little bit rough, and not necessarily because you didn't know what you were doing, but sounds like it was a little bit tricky, especially without a stylus, to draw a very nice graph. So um, I guess I'm not sure what to say. You're listening to this on Thursday at the earliest, and I'm recording it on Tuesday. So maybe by the time you're watching this, I'm already done grading, or maybe I'm still struggling and trying to figure out how to get this thing graded. But in any case, we're moving on to the last new section of the school year, and the section we're doing is literally a section about sections, specifically these things called conic sections. And what I mean by conic sections, or what mathematicians mean by conic sections, are cross sections that you get when you take a cone. And actually, technically, we should think of this as two different cones that meet at a common vertex. And these cones are infinitely tall. So we're seeing one small section of them, and depending on how we slice them, we get different sections. If we slice it, um, I guess we'd call it perpendicular to the height or parallel to the base, even though they're infinitely tall, we get a nice circle as a cross section. Think of this as like a block of cheese, where if you've got a conical block of cheese, which I realize as I say it is probably a weird idea, but if you had a cone and you slice it, send it through one of those meat slicers at Jersey Mike's, and as you're slicing it, parallel to the base, you're getting these circular sections, circular slices of cheese. It's making me hungry. If we tilt it a little bit, if my slice still goes through the cone, but it's not perfectly flat, we end up with a shape that's called an ellipse. And we will spend a couple of days, I suppose, next week dealing with what an ellipse is and how it works and what its properties are. There's some interesting things about that. If my slice this is hard to describe, but it's actually parallel with the slant of the cone, we get a shape that's called a parabola, and we will not be doing a lot with parabolas, mostly because we've already done a lot with parabolas, uh, quadratic formulas and all that stuff that we did earlier in this class, but that is a conic section. And then if I have a slice that is even steeper than the same slope as the slant of the cone, we get a shape that's actually separated into two parts. We got part of it up at the top and part of it down at the bottom. This is a shape known as a hyperbola. Not to be confused with hyperbole, which is a term from language arts. Hyperbole is when you, I guess, exaggerate something with the intention of emphasizing. For example, if I said the sophomore class this year is the craziest group of kids on the face of the earth, probably not true. I certainly don't think it's true, but I'm trying to say that the sophomore class is just really a crazy group, which, by the way, I do not believe. I happen to like a lot of the members of the sophomore class quite a bit. Um, if we look at each of these cross sections laid out flat, I've got a couple of them ready to go here already. Of course, a circle, you guys know what a circle is, a little bit less lumpy than the one that I've got drawn here, though actually that's not bad for a circle, free-handed. And then an ellipse is elongated, either wide or tall, more tall than a circle. We certainly know what a parabola looks like. And then finally, the hyperbola, again, has two parts to it. It is symmetric, not necessarily over the x-axis like I've got shown here. We will come back in, I guess, a little bit less than 2 weeks, probably late next week. We'll take a look at a hyperbola, what its definition is, how we find an equation. But these are the conic sections that we're going to be studying. Before we get into the specifics of the circle, I'm going to remind you of this thing called the distance formula that really is from the Pythagorean theorem. If you learned this in your geometry class, I'm going to guess that your geometry teacher went into how the Pythagorean theorem is where the distance formula comes from, and I'll show you that in just a moment here also, but hopefully this looks familiar. The difference in the x values squared plus the difference in the y values squared, and then take the square root, and that gives us the distance. What that's useful for with a circle is that a circle is defined as a set of all points on a plane that are all the same distance from a point that we call the center. And so this radius is a constant value for any circle. The distance from any point xy to the center of the circle, and I'm not sure why the letters h and k are used, but they are. The center is hk, the radius is r, and then any point on this circle has coordinates of x and y. And so as I think about this in terms of the distance formula, or actually I'm going to go with the Pythagorean theorem, if I draw in a right triangle where I've got a horizontal and a vertical section, of course those are perpendicular to each other, this length right here, the base of this triangle, is the quantity x minus h. And if I put it over here on this side, you might say that it's h minus x, but it's not going to matter because we're going to take whatever that distance is and square it. So if I say x minus h or h minus x, we're going to end up squaring that. It's not going to make a difference. I'm going to go with x minus h to say the distance from h to x. The other part of the Pythagorean theorem, the vertical section here, this is y minus k. A squared plus b squared equals c squared. Here's the horizontal distance, here's the vertical distance, and of course the diagonal distance, the length of the hypotenuse, is my radius squared. And so this is our general formula for a circle. X minus h squared plus y minus k squared equals r squared. And so our focus today is going to be in going back and forth between um, an equation that looks like this and figuring out what the center and the radius are, or given the center and the radius, how do I write down an equation? But this is the important part that we see, that if I have x minus h squared plus y minus k squared, the center is the point hk. I've got x minus the x value, y minus the y value. The x and y values are h and k, and of course my radius is r. The number that's over here by itself is the radius squared. So if I have a circle with a center at 0, 0, I've got a couple of circles at center of 0, 0. Little inside behind the scenes information. As we've been planning the rest of this year, I'm sure you've noticed that we don't have school on Wednesdays anymore. We've had to cut some stuff from our curriculum. And so as we talk about what we can cut and what we can't cut, one of the things that Miss Muser and I, who are the teachers of calculus at this school, one of the things that we really wanted to emphasize was a circle with the center at 0, 0, because that's something that comes up actually quite frequently in calculus, at least relative to the other stuff that we do. But anyway, if the center's at 0, 0, that means h is 0 and k is also 0. This is h minus 0, excuse me, x minus 0 squared. That's just x squared. I've got y minus 0 squared. That's just y squared. And then equals the radius squared. If the radius is 9, the radius squared is 81. And so there we go. I've got an equation for a circle centered at the origin with the radius of 9. Center of 0, 0 with the radius of 0.4, similar left side, actually identical left side, x squared plus y squared equals 0.4 squared is 0.16. And so if you graph this on your graphing calculator, you'd have to solve it for y equals, and you'd have to do some manipulations, but you'd have a circle with the radius of 0.4 centered at the origin. Moving on to ones that are a little bit more complicated, not too crazy. The center is at 3, negative 1. All right, well, our x value, the h of our equation, is 3. So x minus the x value, x minus 3 squared, plus y minus the y value. Well, y minus negative 1 looks like y plus 1 squared, equals the radius squared. So equals 3 squared equals 9. This is the equation for a circle centered at 3, negative 1 with the radius of 3. And then I'm going to peek at the rest of these. Oh, they're all pretty similar. I might just go down to this one so we can see this fraction at work. My equation is going to be x minus the x value, x minus 8 squared, plus y minus the y value, y minus 0 squared, equals the radius squared. Well, the radius is 8/5, so the radius squared is 64/25. And there we go. As I look at the other two, there's nothing too crazy about those, so I don't feel the need to do those as further examples. You'll get plenty of practice with the homework tonight. And so if I say, write an equation for this circle, radius of center at -2, -6, radius of 11, and then give 4 points that are on the circle, well, let's get the equation down first. X minus -2, x minus the x value squared, plus y minus the y value, y minus -6, looks like y plus 6 squared, equals the radius squared, and 11 squared is 121. Now, there are an infinite number of points that are on this circle. There's an infinite number of solutions to an equation like this one. I want to talk about the 4 easy ones to get. The 4 easy ones that I'm going to get are going to be, well, suppose I'm at the center, I'm at -2, -6. I can go any direction 11 and get to a point that's on the circle. So I'm going to choose some easy directions to go. I'm going to go straight up. If I go straight up 11 units from the center of this circle, my x value won't change, and my y value will increase by 11. -6 plus 11 gets me to 5. Straight down from the center, again, my x value stays the same, but if I decrease the y value by 11, we'll end up at -17. And by the way, if I want to verify, if I'm not sure if this is right, I could plug these numbers into this equation. And if I plug -2, 5, well, why not? Let's plug it in. -2 plus 2 is 0. Nice. 5 plus 6 is 11. 0 squared plus 11 squared is 121. Sure, 121 is 11 squared, so it works. But that's only 2 points so far. Let's move on and take a look at some other points. We can also find points by keeping my x value of the center constant. Let's keep the same vertical distance, but now go to the left by 11 units or to the right by 11 units. Let's take that -2, the x value of the center, add 11 to that. -2 plus 11 brings me to 9. Or, again, keeping the y value at the same value as the center, if I move to the left, I'm taking -2 minus 11 to get to -13. Those aren't the only points. In fact, there's an infinite number of them, but those are the easy ones to find. Straight up, straight down, to the left and to the right. Up, up, down, down, left, right, be a start. And then going in the other direction, if I'm given an equation, I should be able to find the center and the radius just by knowing the form. I've got x minus the x value. My x value must be 4. Y minus the y value. Well, y plus 6 is y minus -6, so the y value is -6. And then my radius, well, this 36 is the radius squared, so the radius must be the square root of 36, which is 6. Just like with amplitude, you can never have a negative amplitude. We can never have a negative radius either. And so we'll just take the positive value for that square root. For the next one, x squared plus y squared equals 80. Well, looks like my center's at 0, 0, because I've got x minus 0, y minus 0. And then my radius, I'm going to write it down here. This is the square root of 80. That's going to simplify. Either a decimal approximation on your calculator, I'm not sure what it is, but it's probably about 8.9. Or if I want the exact value, I can look for perfect square factors. I think 16 goes into 80. I'm just going to pull out my calculator here and verify. 80 divided by 16. Yep, 80 divided by 16 is 5. So I've got the square root of 16 times 5, which I can write as the square root of 16 times the square root of 5. I've got a couple other examples here. Again, I feel like this one's maybe a little superfluous. Let's go straight over to the last one that I've got here. I've got x minus the x value. The x value is 0.6. I've got y minus the y value, but y plus 0.9 is the same as y minus -0.9. And so my center is 0.6, and negative 0.9. And then 2.25 is the square of the radius. So the radius is the square root of 2.25, which I can plug into a calculator, or maybe my number sense is such that I know what that is, but it is 1.5. And then I'm going to continue on using that same equation and talk about how to get those same 4 points. Now again, I remember that my center is at -6, -0.9. I'm going to write that up here. This isn't one of my answers, but my center is at -6 and -0.9. Oof. And my radius is 1.5. And so my 4 points, the one that's straight up, I'm going to keep my x value the same, 0.6, and then I'll take -0.9 and add 1.5 and get up to 0.6, positive 0.6. If I go straight down, my x value is 0.6 and my y value is -9 minus 1.5. I think that brings me down to -2.4. If I go straight to the left, my y value stays the same at -0.9, but my x value is decreasing. 0.6 minus 1.5 brings me to -0.9. Interesting. And then if I go straight to the right, my y value stays the same at -0.9, but my x value increases by 1.5. 0.6 plus 1.5 brings me to 2.1. And so those 4 significant points are on the circle, which will help me to graph equations like this one. Graph this equation. I am going to first figure out where the center is. The center is at -4. X plus 4 is the same as x minus -4, so the x value is -4. Y minus 2, the y value is 2. And then my radius is 5. So the point -4, 1, 2, 3, 4, up 2, there is my center. And then my 4 significant points. Yeah, I know what a graph, what a circle looks like, but it's going to be easier if I have some points on here. So from the center, I will go up 1, 2, 3, 4, 5 units. I'll go to the right, 1, 2, 3, 4, 5. Go down, 1, 2, 3, 4, 5. And to the left, 1, 2, 3, 4, 5. Now, if you're like most of my students, the first time you draw a circle that goes through these 4 points, you're going to get a circle that looks a little bit on the lumpy side. And so my advice for you when you draw these circles is think about, as you're going through this point that's the farthest to the left, at least at that moment when we pass through that point, this graph is straight up and down. At this point, the graph is straight up and down. I realize it's just for a moment and it's going to start to curve right away, but at least for that moment, it's straight up and down. Or in the case of the top and the bottom, it's straight to the left or right. And if you think about that, if you're heading at least in this direction before you start to curve, if we think about approaching that next point so that it's vertical, we'll get something that's at least a little bit more circular. Coming straight down, but then gradually curving so that it'll be horizontal by the time I get there. Going straight up, but curving around, so it's going horizontal by that point. And you can definitely see, just like with my sines and cosine curves, this is far from perfection, but it's also a lot better than a lot of examples that I've seen in the past. Not looking for perfection, just looking for something reasonable, like I'll be looking for on the test that I'll be going to correct right about now. So there we go. That's the start of the next chapter, the last chapter, the conic section chapter. We'll be doing more with circles tomorrow, and then moving on to ellipses and hyperbolas next week. Hope you're having a great day. Hopefully the weather's looking as good as it is today as I record this on Tuesday, but I guess that remains to be seen. I'll finish time traveling by the time you're watching this. So have a great day, and let me know if you have any questions or comments. Bye-bye.